Good afternoon. I'm Tim Meehan, and I'll be talking about APIs and community in the composable data ecosystem. First, a little bit about me. I work on Presto, which is an open source distributed query engine. I'm the TSC chair of the Presto Foundation, and I work on Presto and data lakehouses professionally at IBM currently, but also previously at Meta. As part of this job, I've contributed features to Presto and the surrounding ecosystem, supported it in production, and also supported the open source Presto developer community. So I wear 3 different hats as part of the Presto project. So let's get started on what is the composable data ecosystem. There was a great paper at VLDB last year that was written by Pedro Pereira, Wes McKinney, and others that outlines it, and I'll give it a brief quote. It is a vision that by decomposing data management systems into a more modular stack of reusable components, the development of new engines can be streamlined while reducing maintenance costs and ultimately providing a more consistent user experience. So what does this mean? If you split up the database into modular components and share them, you can develop a better database. So that's essentially the thesis, and this, I think, needs to be proved out, but it's pretty compelling. This might seem like a novel concept, but there's actually a good chance that you're already using decomposed or split up components, and this can be seen in a number of trends. One trend is the splitting of the storage from compute. So the migration from enterprise data warehouses into cloud data warehouses. The second is splitting ingestion from query. So in days of yore, you would use a single tool for your ingestion as with your query. But these days, it's not uncommon to see Spark be used purely for ingestion and a tool like Presto, Trino, or Impala to be used purely for your query, in addition to other tools, maybe even custom programs. So the splitting apart of different interfaces into the data lake is another trend where this used to be one tool, but now we have many tools that do this. And then the third is the catalog. This used to be a built-in component inside of a data warehouse. It's moved into a separate service through the Hive Metastore, and now we start to see innovation in catalogs through recent trends like the Iceberg REST catalog and Polaris and Unity. So there's a lot of recent development, which is very exciting. So what is motivating people to split things up? We talked about the move from enterprise data warehouses to cloud data warehouses, and that's really driven by cost. By splitting up the data warehouse into separately scalable storage and compute portions, you can reduce costs because your storage will most likely scale at a much faster rate than your compute. So this gives you much better efficiency and will help you to reduce your costs. Another way that you could separate your storage from compute would be to use a data lakehouse architecture where there it's also very common to have a separate query and unmanaged or externally managed data lake in a cloud data provider like Amazon or Azure. The second is performance. So by separating your ingestion and your query layers, you can optimize different systems for these use cases. So in the example before with Spark is very, very highly optimized for batch ingestion, and tools like Presto, Trino, Impala, and others are optimized for real-time querying. So things like analytics, ad hoc queries. Each of these systems are designed with those use cases in mind, and so it's very common to use different tools for ingestion and query and others. So you tend to get better performance by using the right tool for that use case that it's designed for. The third is flexibility. So by disaggregating components, you can mix and match where needed. And just go back into the compute engine example, these days it's easier than ever to switch out a compute engine when needed. We'll get into the reason for this in an upcoming slide, but by splitting up the database, you can now upgrade certain portions of it without upgrading the entire system. So it gives you much better flexibility. And finally, you have better innovation. You can develop specialized components for particular use cases by splitting up the database into these individual specialized systems. So whereas a SQL-only system would be relatively difficult to pigeonhole into certain AI use cases, by allowing these to be separate over a common storage layer, you now can introduce specialized ML and AI use cases onto your data lake, whereas with this single system, this would be cumbersome. Is there any way to quantify the effects of this disaggregation over the past 20 years? One heuristic to look at is to simply look at what we call the MAD landscape. The MAD landscape is a curated list of data and AI projects that's been taken nearly every year since 2013 by Matt Turk. And here's how it looked like in 2013 when it first came out. The one that I think is most relevant to us is the one on the bottom. So these are open source projects, tend to be data related projects. And if you look at 2024, this has happened. So over the past, just over 10 years, you can see that the number of projects in this open source infrastructure, orange sliver right here, has grown exponentially, just like the rest of the landscape. So the paradox then really is, given that it's 2024, why do things work more cohesively than they ever have? This might be a bold statement, and perhaps others disagree, but I think if you're using a table format like Iceberg, Hoodie, or Delta Lake, then you're finding that this has solved real challenges, and this is bringing some sense of order to your data lake. Why is it that in spite of the increase in data projects, we actually have better cohesion within our data lakes? And the chief innovation here, I think, is the transactions that these table formats bring. So transactions get rid of phantom commits and make it so that people don't get partial reads, which could have been a problem for Hive in the past. But in addition to bringing consistent ACID transactions within a single engine, they also now bring it to every other engine who happens to be operating inside of this data lake. And so we now have this phenomenon where, thanks to ACID transactions, your compute engines could be a streaming engine like Flink, a batch-end streaming engine like Spark, or a query engine like Presto, can really operate over the same tables and not get in each other's way. So I think that this is the chief innovation, that table formats, it's much discussed, but just to set the stage for future slides, I think that that's one of the chief innovations that table formats have brought, which is a sense of order to compute engines operating in a data lake that didn't exist before. And just to hammer this point home, you now can have pollers, Presto, Spark, Flink, and Redshift really all operating over the same data lake cohesively, which is just something that would have been kind of crazy to think about maybe a handful of years ago. But are we done? So if we think of these table formats as being the bottom half of the database, so the table formats have really brought order to things like compaction, transactions, the things that you associate with the storage component of the database. We're now seeing a somewhat rapid convergence towards standards in this area. But what about the top half of the database? So what about the compute engines, and what about the user-facing aspects of the data warehouse that we've been splitting up all this time? And the answer is no. So we have, I think, a few fundamental challenges in this area. The first is that there are very large language barriers. If you, as it was mentioned before, you might be using a batch ingestion engine together with a query engine. If you use these two in conjunction, then they will have slightly different SQL with slightly different semantics, and that does not give you the sense of cohesion. So there are language barriers. So we have split up aspects of the data warehouse into different components, but these different components are not consistent in their definition of the language. So there is more work to be done on bringing consistency in the language that you use to interface with the warehouse. The second is that when these systems do interact with each other, they interact through what we can call glue code. So Presto and Trino connectors. Spark also has a connector architecture. Many different compute engines now have a way to plug in interaction with different storage units, and they each require their own independent glue code. And this independent glue code is difficult to maintain and is proprietary to the system that you're writing the glue code for. So this makes it difficult to have a cohesive front-end experience for the data warehouse. And then finally, there is unresolved complexity, because if you use two different engines for your ingestion and for your query, you now have Spark only problems or Presto only problems, and this will cause more overhead and maintenance for whoever is maintaining the data lake. So there's a complexity issue as well. There are some solutions out there that are attempting to solve some of these problems. So there's a very interesting project called IBIS that gives you, it doesn't speak in terms of SQL, but it does speak in terms of data frames. And IBIS will give you a consistent data frame language that will then compile to different SQL backends. So that is a very convenient thing if you're using data frames, and that's a good start. There's projects like Substrate, where the hope is that by engines integrating into the Substrate API, then you can mix and match SQL parsers and plug that into Substrate for downstream execution. But there's not a lot of adoption yet. And there is Presto and Spark, which allows you to use Presto SQL inside of the Spark runtime. And so this solves, if you're a Presto user and a Spark user, this solves your problem because it allows you to run your Presto SQL inside of Spark but it doesn't solve the problem for any other engines that you might be using. So there's a lot of kind of like in-flight solutions, but there's nothing that solves the problem yet for the user of a multi-tenant data lake. There are standards that are being developed, such as Aeroflight and Aeroflight SQL, that allow you to transfer data between different systems. But this data transfer might suffer from a few problems. For Aeroflight, there might be the problem of the flight service having custom commands which need to be understood by the originating system, which inhibits the adoption of that protocol, and Aeroflight SQL, which is implemented for a few data management systems, but is SQL oriented, so it doesn't work for non-SQL systems. You also have projects like VLOX and Data Fusion. So the paper that I mentioned earlier very prominently mentioned projects like VLOX and Data Fusion merging the execution engine aspect of the SQL frontend, so that you have at least a single component that does the calculations that power the SQL query. So work is in progress to start using VLOX and Data Fusion, but we're not there. There are projects that are off the ground and getting started, but we don't have widespread adoption yet. So this is still very much a work in progress. So we've taken a look at many of the projects that are being worked on that aim to bring a better sense of coherence and standards to the compute portion of the data lakehouse and data lakes. But let's take a moment to examine what makes integration challenging. So what are some of the challenges that maybe some of these systems experience, or that are challenging for some of these projects? And the first one, I believe, is the lack of clear API. So if your project doesn't have a well-defined API, then interoperability will be challenging, because the integrating component will choose to integrate in a way that involves the least amount of resistance for that component. One example is Hive views across Presto, Trino, and Spark. For Presto, views are stored in one particular way, and Spark views are stored in a different way inside of the Hive metastore. Because of this results in incompatibilities when you attempt to list out views between those two engines. So that's just one example, but in general, without a clearly defined API, engines will choose to integrate the way that just makes the most sense, and if there is no clearly defined guide on how to go about that, then that will result in local decisions being made for each integrating component, which will result in a lack of cohesive user experience. The second is you might have an API, but it might be an overspecified API. And so if you have an overspecified API, then it will be very difficult to integrate that API, which will limit the adoption. One good example of this is actually the SQL standard. The SQL standard is often described as something that engines will strive toward, but it might be difficult to completely implement because the SQL standard is so expansive. There are 7 books to the SQL standard, and the implementation costs for implementing it completely typically are far outside of the reach of most companies and open source projects. So you tend to have language that revolves around a project striving towards standard compliance, which means that there are plenty of unspecified behaviors between the projects, which will mean that you effectively have to migrate from one database to the other. You can't just simply reuse your SQL. And then finally, you might have language or protocol adoption barriers. So one good example is using a JVM component with a non-JVM component. Because it is, when you attempt to bring a JVM component into let's say a native or a C++ project, you also have to bring a JVM. This means that effectively, much of the Java code that's been written in the big data ecosystem cannot be used in more optimized native systems, which limits the adoption of that code. So what are some of the things that can go wrong when you're designing an API? Once again, the choice of language could inhibit adoption. The wrong protocol might inhibit adoption. So protocols such as Thrift are in many ways quite useful and enable you to make a lot of progress on your service, but they might not have a lot of adoption outside of certain companies. So Thrift might enable you to develop the component quickly, but it might inhibit adoption because for you to take on that project, you suddenly need to understand how to troubleshoot and support Thrift. And finally, probably the most important part is community engagement. So when you develop an open source component, you're not just developing the code, but also the framework by which that code gets developed. And if the code is good, but that framework is buggy, let's say it doesn't take in external contributions very quickly, or it is suspicious of contributions from people outside of a certain company, then that will also inhibit adoption, because when other open source projects or companies adopt that component, they will be making the calculation of where this project will be 5 to 10 years from now. Can they upstream some of the changes that they may be making to that project so that they don't have to carry on a fork forever? And is it possible to influence the direction of that project? So there are more considerations around using a component besides the utility that it brings. It's also the long-term direction of the project that you're also really signing up for. So community engagement, I think, probably is the most important thing possible when you're designing an API, because it's really not just about the API that you're designing itself, but also the framework by which you change the API, which is needs to be flexible and needs to have good habits. So let's talk about some best practices or things to look out for when you're designing or looking at an open source component inside of a data lake. The first one is you really want to make sure that you are using a protocol. If you're using a service, that you're using a protocol which is universal, and typically this will end up being REST. Almost any data infrastructure project will support REST. Will have infrastructure around REST, and REST is very, very widely understood by both folks in the data community and in the non-data community. So REST is a very good choice, I think, for designing a protocol over things such as Thrift. The second is, in this day and age, the big data ecosystem began really being JVM oriented, but I see that that's very rapidly not being the case, and we are seeing a lot of movement in C++ and Rust-based projects. And so I think the days of developing JVM-based infrastructure are slowly going away, and if you are going to be developing something that is meant to be shared across multiple components in your lakehouse, it really should be in C++, because by it being in C++, it can be shared across a wider range of data infrastructure projects, C++ and Rust. The point is, I think that these projects should be native, just to prevent, introduction of the JVM where possible. If your project is using storage, then there should be a spec. If there is a service, there should be a spec. Separate the spec from the code and treat these as two different things, and presume that someone will have to have a different implementation of the code that conforms to the spec. There are so many companies that have particular requirements that mean that they cannot use the code. And by coding to a spec, you also account for the fact that people will fork, but even if they fork the code, as long as there is conformance to the spec, that's fine. It doesn't result in divergence in behavior. So I think coding to a spec is a very powerful paradigm, and I see that the Iceberg community has done that very well. Simplicity and governance. So the open source community that I mentioned in the last slide, that open source community should keep a very careful watch on the complexity of the spec, and should have a good foundation for making sure that changes are reviewed promptly, and that pull requests and updates to the spec are actioned when they're appropriate. So basically having good muscle memory within the community for how to take on external contributions instead of letting them pile up in GitHub is a very important aspect of creating an external service or component in the compute engine space, and that's something that both users and developers should be watching to make sure that the project is on top of that. So, how important are all of these things? So let's take a look at a checklist for how we can evaluate if a component is on the right track. And I think the first one is to ask is how open is the community? Are there established governance for this community? Are all of this, is all of the code coming from a single employer? This is something that sometimes is hard to measure, but it's worthwhile to measure because oftentimes integrating with a component is a long-term decision, and so you want to make sure that there is sufficient diversity within this community to prove essentially that other people can get their changes into. If the component is a library, what language is the library built in? Once again, this ought to be something that's native, I think, in this day and age. Is there documentation for the library, and is the library versioned and tested? So is there a release version for this library, and do they do testing against that release version? Those are very important things to look out for. If there is a negative in any of these questions, then it should be considered carefully. If the component is a service, what protocol does the service use? Going back into our discussion on gRPC, Thrift, REST, and is there an API specification for that protocol? There really ought to be an API specification in general. If the component is a format, is there a specification? So if this is related to storage, there should be a specification for that as well. and does the component rely on undocumented behavior? So, for good interoperability, the behavior of the system as it interacts with, other components should be very well documented. And if there is undocumented behavior, that should give cause for concern. So as I mentioned at the beginning, I work on Presto. And so why am I talking about disaggregated components so much? And the reason for this is because Presto itself is in the middle of being split up even further into multiple subcomponents. Let's take a look at Presto's current architecture. There is a coordinator which takes a query, parses, plans, and schedules it. And there are workers who execute data plane fragments over some sort of remote storage. This is a very, very simplified view of Presto's architecture. So here is, one example of how it could look like with if I'm operating over Hive. And what we're in the process of doing is swapping out the native or the Java-based execution engine with a native execution engine, so C++. So we are integrating with the vlox project to do the actual query execution. There are many different reasons for doing this, but some of them I already mentioned, where we're specializing and we're getting tremendous performance benefits by using the vlox project for execution. Some people use a third of less hardware for the equivalent performance, so they optimize for cost savings, and some folks use the improved performance to lower query execution times. And also, by leveraging vlox, we can be a lot more competitive with more online-based systems than we could previously. Also, by focusing on our execution engine on vlox, we have a lot of converged efforts. So, for example, it's not just the Presto community who develops on vlox. There are companies who use vlox. There are other open source projects who use vlox. And so what we find is that we get a lot more development from this bigger network of individuals who are all working on this common execution engine than we would just within the Presto community. So one of the the architecture behind this is essentially is that I'm just going to take a Java worker and swap it out with a C++ worker. And this sounds good in theory, but why can't you do that? And the reason for this is that both the analyzer and the planner need to know something about the worker that's underneath it. So, instead of, it's a little bit more involved than just having a worker process pretend to be a Presto process under the hood, because there are differences, such as not all functions in vlox are actually implemented. Not all Presto functions in vlox are actually implemented. So there are some function differences between the two engines. So there are some session properties that are slightly different. Some of the plans might not be compatible with each other just because of some of the design choices made by the vlox community. The connectors that are compatible might have differing levels of compatibility. Some of the aggregation function metadata might be different. So there's lots of little differences that pop up between the Java Presto cluster and the C++ Presto cluster. So the lesson learned here is that we didn't fully appreciate the level of knowledge that is required inside of the whole Presto runtime that needs to know about the underlying capabilities of the C++ worker. And so really what we got wrong, or the lesson that we learned, is that the task API, which is the API that the worker communicates with the coordinator, is not sufficient. So it is required but not sufficient. There is additional deeper API that is required to do this communication between to function cohesively between the C++ worker and the Java worker. And our solution for this is to treat the what we call the eval, or the worker component, as a plugin. And this plugin will be hooked into all of the aspects of the Presto runtime that require that knowledge. And so instead of the C++ worker kind of like being a drop-in replacement, it'll be a deep integration inside of the entire Presto runtime. And here we have a diagram of how this will look schematically. So we have cohesion between the Presto coordinator and the native worker in terms of the functions that are supported, the types that are supported, then other things as well. So we have good bidirectional communication between the C++ worker and VLOX with the Presto Java coordinator. I'll end it here with some speculation on what the future might hold for new data projects that might get spun up. One pain point that one experiences when hopping between SQL engines is the functions that they support. So you might move to a new engine, or you might be switching between batch and interactive, and you might find that a function they use for one isn't present in the other. So I think now that we're in a multi-tenant and a multi-tenant lakehouse world, it makes a lot of sense to share functions between systems. So it wouldn't surprise me if a new project popped up that started doing that. Another one is a shared optimizer. So in a world where you have multiple engines which are all operating over the same lakehouse, which has the same access to statistics, it really would make sense to have a common optimizer between engines that gave you a cohesive experience as you went from one engine to the other. And then finally, the SQL that one uses between different systems right now is different. It would be, I think, a very positive direction to start using a common parser that engines would then adopt and use, so that the same SQL is shared between multiple different engines, so that people don't have to rewrite their SQL queries. So a common front-end component, I think, would make a ton of sense. And I can't predict the future, but I would be very, very happy to see such a project spun up. And regardless of what projects do get spun up in the next 5 years, I do think that as developers and as users, we need to keep in mind that APIs are really the foundation of this multi-tenant lakehouse that we are using and building. So APIs are really what make the user experience of these disaggregated components, gives them the look and feel that they have. So APIs are very important, and as these APIs are being designed, simplicity, the appropriate level of detail, and good governance, including a good open source hygiene, are very, very important. So I think as new projects get spun up, we will see more and more maturity around this, and I think that this will be a good thing for the data lakehouse. And that's it for me. If you want to read more about Presto's evolution, check out our blog. We have lots of articles about the move to C++ and some of the work that we've been doing lately. So definitely encourage you to check that out. And I wanted to thank you for your time and hope to see you soon.